understand why not come back to the encapsulation of the code, but I just had a while where the condition based on the number of units played, and then I just had building to switch plays. That's like 2 lines code rather than 3 lines missing. Now we don't do all those until next semester in
Yeah, I mean, it's a bit funny because I tell you that. Yeah, they just sort of tell you what's weird and how certain parts and they're not teach, they're not really learn much, they're using this parallel to what's being code and all that.
So for those of you wondering why we haven't started yet, it's normally custom at TUCS Talks to start at 7 past the hour and not right on the hour like lecturers do. Yeah. We say 1 o'clock, but nobody shows up at 1 o'clock. Yeah, exactly. This is the pain when people got sharp on time.
which is yeah. I understand that, and that's the thing that it's, maybe you can have programming starting in the basics and then show it for you how that cycle works. It's not like it's doing it, it's like what we're doing. But their idea was going on exactly the same thing. Yeah. So yeah, I'll take this one class 40 or specific. Some of those parameters in the
Winton, sup? Oh, okay, that's why everyone's late. Okay, we'll give them a moment to...
give the icon.
Yep.
We had lots of themes, so probably going to look out flexible learning space.
Pardon?
We're going to look out flexible learning space underneath this for next line. Apparently it's similar cost to law and it's bigger.
Who's spoken?
They talked to Ingrid, who spoke to someone else. Or no, Ingrid told them to go to someone else, and it's $20
Right.
an hour, blah, 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 blah.
Okay, yeah, so the deal with that space has always been for us that if we wanted to book that room, we would need to book the foyer as well.
Oh, apparently you can get external access to it or something. I don't know what's.
Oh, it's...
Like, the cost of a quota was $20 an hour, which I assume
Okay,
Queensland
there's
gets similar.
been a couple of things. Firstly, there's that we were told we had to book out the foyer, and the second was that we need to pay for ITR to remove the computers from the room,
Oh, right.
which is why we've never used there.
Sure. If it only costs us what they quoted us, then I wouldn't worry about it.
Yeah, that's fine.
Yeah, they said $20 an hour, which I assume is the weekday and the day rate.
Yeah.
And weekends at night time would be probably some sort of.
Okay. Yeah, I'll...
But
You do it right.
the Ducky was writing down some of the stuff. So.
Yep, that's cool.
But we're going to have 4 tournaments running. And we're going to have
Sure.
3 societies. Captain Planet Land. See what happens.
Captain Planet Land. Oh, right. That almost makes sense.
Yeah, you can't call it a CP land because that's something different.
Wait, what?
Exactly. That's also that. That's that one.
Was this actually a real thing?
Yeah. Yeah. Starts with a nervous breakdown on flights. It was screaming about a bombing model. So they had to trick you out of the cockpit, where a bombing model happened to be ground by a corrections officer. It just happened to be flying. This is awesome. It's like the airline. Yeah. Shall we get started without them? Okay, thanks everyone for coming along to the first of our Tech Talks for 2012. My name's Chris. I started these off back in 2008. And since then we've had a whole heap of talks presented by TUCS on various topics relating to computing. And the ones that I've tended to present are fairly high on technical content. And that's true of today, except that I'm sort of going for something slightly different.
Steve is also an ideas man. That's why Dad called him the ideas man. He has lots of ideas.
It's a motorcycle helmet with a built-in brake light. You are an ideas man.
So this is an ideas talk more than a technical talk. Basically, I find myself presenting on really deep technical topics far too often, and I thought it would be more interesting to give a high-level overview of how things are happening in computing at the moment. Basically, as computing students, a lot of what you tend to do involves writing code and things, and from first year through to third year, what you tend to code in is Java. And, you know, spending too much time writing code in one language tends to result in you not having an idea of the bigger picture that's happening in computing. So I'm sure you're all familiar with Java. This is because it's taught in first year and in second year and in third year, and for a lot of you also in honours. It's also a really widespread language in business, and the fact that Java is everywhere means that it also influences a lot of other aspects of computing. Now, I have really strong opinions on Java as a programming language, and most of these aren't really fit for reproduction in a tech talk this year. The main reason for that is because I gave a 15-minute tech talk on it several years ago, and it's recorded. You can get it at this URL here. And everything I said in it is pretty much relevant today. So I strongly urge you to go and check that out, because it contains most of my opinions on Java as a programming language. So with the fact that I don't particularly like Java in mind, I find myself in a bit of a predicament at the moment. And that's that for the past year and a half or so, I've been working more or less full-time as an Android developer. Now, Android's a pretty good platform for developing software, and there's quite a programming community out for it, and it's really well supported. But the programming language that is used in Android is Java. And so it's with that unfortunate truth that I find myself being effectively a full-time Java developer these days. And it's that thought which has pretty much inspired my talk. What I'm not going to be talking about today in any great depth, however, is Java. Instead, what I want to sort of explain is the following. The first is, where did Java come from? The second is what sort of family resemblances there are in Java. And the third is to ask where Java is going. Have you finished?
Something very humorous.
I asked Google Images to where are we going, and that's what came up. So those are the three things that I thought I'd ask in this talk and do a bit of research on to see what I could find out. So the first thing we need to do is look into the sort of history of Java itself. Now, the original idea for Java originated at Sun Microsystems in 1990, and the first release of Java itself didn't come out until 1995. Now, lots of things came out in the time between Java 1.0 being released and now, and most of those have been pretty epic failures, right? Lots of things have come and gone in computing. So the amount of time that Java's been able to stick around for is quite astounding. It's 22 years old now. And in terms of tech ideas, this is like a grandfather. It's old enough to be a grandfather. You know, like all good children, Java has had its children, and the children of Java have had its own children. So a good 2 generations of programming languages and platforms that have descended from the ideas of Java. But the thing is that Java itself is still used as a platform, and it's still thriving as a platform. And so it might be instructional to see why that might be the case. So the first question that you'd ask is, what is Java? What am I talking about? Because Java itself is actually several pieces of technology, and these work together. It consists of a programming language, a series of tools for distributing software, and a runtime environment. So you're probably familiar with Java, the programming language. A sample piece of code in Java might look something like this one that prints hello world, which I'm sure you're all familiar with. They originally set out to come up with a language that was pretty much similar to C++, but with several of the important complicating factors of C++ removed. This was because at the time C++ was perceived as particularly complicated to maintain code for. This is probably a fair assessment. Maintaining a C++ project is insanely difficult in my opinion. But what ended up happening was an entirely new language with features that were parallel to C++ rather than derived directly from it. So it built up from the ideas of C, but it invented its own design for object orientation and several other features that C++ had come up with. In particular, something that Java did was force you to have an object-oriented structure in your code. It forced a file structure upon you. So you have one primary class or interface per file in Java. And all of the code that you would write would have to exist within the context of a class. You can compare this with C, where all the code that you have to write must be within a function, or as a slightly less extreme example, Python or PHP, which, whilst it's object-oriented, the object orientation is optional, and there's no structure enforced upon your code at all. The other thing that Java did that was unique to languages that inspired it was to have its own built-in automatic memory management in the form of garbage collection. This is a departure from C or C++. If you're studying or have studied algorithms, you'd know that you have to do manual memory allocation in those languages, and it's remarkably difficult to get right when you do it. So instead of having manual memory management, Java has automatic memory management in the form of garbage collection, which eliminates a whole set of bugs. And something that people don't necessarily consider when they're thinking about Java, or at least starting off in it, is that Java did a remarkably good job at solving the issue of distributing code for other authors to use. Instead of having, if you've coded in C or C++, you'd know that you'd include header files at the top of your source code, and that would get built in by a preprocessor. And then later on, you'd have a linker which would take a precompiled shared object and whack that into your binary. Java doesn't need to do that. Instead, precompiled class files can be analyzed by the compiler. So the compiler can tell what the API of a class is from a precompiled unit, and the Java runtime can pick up class files and build those in at runtime. So it actually makes it very easy to distribute library code in the form of either class files or zipped up archives of class files known as jars. So the Java programming language itself also has numerous bad things, and once again I encourage you to look at my talk from a few years ago on what I think is bad about the programming language, because it's not something that I'm going to dwell on during this talk. So the second part of Java that people consider is the software platform. Basically, this is a set of software that lets you run Java code. And they had this slogan when they released it, which was to write once and run anywhere. The reason for this was back in the early 90s when Java came to exist, there was still an arms race in processors going on. In the desktop space, there were Intel 386 processors. Apple computers were running on things like the Motorola 68K and was in the process of transferring over to the IBM Power architecture. And in the server space, there were things like SunSpark processors, Alpha processors, IBM Power processors, lots and lots of different processor architectures. And that made getting your software to run on various types of computer a real bitch. So one of the original aims for Java was to market to cable television companies to provide set-top boxes to manage to provide management software for set-top boxes. So the idea being that they could say, hey, look, you've got all these really obscure devices from weird Chinese processor manufacturers that you haven't heard of. Wouldn't it be great if you could run the same software on all your boxes? So the only issue would be getting Java to run on the devices that they needed. None of the cable television companies actually picked this up, but that's beside the point. The other advantage would be that you could run your enterprise applications on any hardware that you bought, because there was still this processor arms race going on. And so you'd be able to save money from being able to select whatever hardware you wanted that matched the configuration that you needed. And they also decided that Java would be good for mobile phones. They released a smaller version of Java called Java ME. I have opinions on this, and there's a reason why nobody uses it anymore. But that was one of the things that they came up with. And the enabling thing that would let you run Java on all of these things was a piece of software called the JVM, or the Java Virtual Machine, which is basically a computer that's defined in software that has its own machine code, which isn't particularly related to any of the processes it targets, and just has a small translation layer that goes from the bytecode or the machine code for Java and would target the process you were running it on. And the way it did this was through a language called Java bytecode. Java bytecode has a lot of interesting features about it, which is different from other virtual machines. The most important is that if you take apart a piece of Java bytecode, you'll end up with something that largely resembles Java source that could be used to compile it. There's also an interesting feature in the format of it, which is that if you take a look at a directory of Java class files, you can infer the structure of the code that was used to create it. You have one class file per Java class, and those Java class files have the same name as the source code that you used to generate it. This is not something you can do with most machine architectures. And the final thing that the Java VM does nowadays is something called just-in-time compilation. So traditionally, when interpreted languages were just starting out, these would be very, very slow. You'd have to load the source code and an interpreter would operate basically on the representation of the source code that got parsed by the interpreter. And this means that it's very, very slow. A just-in-time compiler analyzes the code that's provided to it and turns important bits like really tight inner loops into machine code ahead of time. And this means that the bits that are important to the performance of your code get run really, really quickly. And what this means is that modern Java code executes in a time that's probably only about 1.5 times slower than the equivalent optimized C code, which is pretty cool. And the final point that is interesting about Java is that since 2006, it's been an open source language, open source environment. The open source community has taken to Java quite extensively in the time since then. If you take a look at the Apache server project, you'll see that most of the code that they publish these days is done in Java. So, in summary, there are basically three things that I think are important to Java as a platform. The first is the use of managed memory in what is effectively a low-level machine code context. This is something that really wasn't done before Java came about. The second is that Java, the language or the programming language that you use to write code that targets the JVM, is very tightly coupled with Java, the software platform, which means that Java bytecode strongly resembles Java's source code. And the third is that it's very easy to distribute code that targets the Java software platform. Be this in the form of library code that you're providing to other developers. It's very easy for them to take some precompiled Java code and whack that into a project, or be it the fact that you can easily deploy it on a multitude of devices. So with that, I want to look at three things that have been developed since Java. It's my intention to show you a few things that have been influenced by the existence and the popularity of Java, and hopefully I'll show you after that how Java is now being influenced by these pieces of software. So the first thing I want to talk about is Microsoft. You probably know them as the developers of Windows and Office and software that you use on a very regular basis. But where Microsoft actually started out was with designing developer products. You should know what this is. Who doesn't? Great. Everyone knows what BASIC is because pretty much everyone who's done any programming has seen BASIC at some point in their life. Microsoft, before they worked in operating systems, spent some time attempting to get a BASIC interpreter included on the IBM PC platform. And the only way that they could end up doing that was if they distributed an operating system with it at the same time. And by the mid-80s, every programmer would have in front of them on their PC something like this, Microsoft Quick Basic. This was the first IDE I used as a programmer and was the first programming language that I seriously looked into. It even has a survival guide, see? And from then on, Microsoft continued building upon BASIC as a programming language for developers to do things with in their operating systems. They released a product called Visual Basic in the late 80s. Visual Basic was a huge success. The original version was for creating effectively graphical user interfaces in DOS, but very quickly after that they came up with a Windows version of it. And by the mid-1990s, Visual Basic was by far the most popular way to write applications for Windows. Now, Visual Basic 5 came out in 1997, right? So if you remember back to earlier in my talk, I mentioned that the first version of Java was released in 1995. See, I said that earlier. So the thing is that Microsoft wanted people to develop for Windows. So what did they do? Well, they took Visual Basic and made a Java development environment out of it. Visual something or other, version 6, even though that was the first version that they released. Seriously. And along with their version of Visual Basic for Java, see, it takes the ease of Java with the power of Windows. That's good, right? So along with Visual J++, they also released their own parallel version of the JVM. Now, the existence of the JVM was actually a pretty good thing. It meant that there was active competition in the design of Java virtual machines, and this is one of the reasons why things like just-in-time compilation came out in the Java virtual machine. This is something that's really important to Java execution these days. Now, I couldn't actually find when the initial version of the Microsoft JVM was released. That was because it's disappeared from history. I know that it was released at least by 1997 because there's documents of a lawsuit from Sun Microsystems, who invented Java, on Microsoft because of the Microsoft JVM. This was because Microsoft didn't quite implement the JVM as specified by Sun, and they got sued for breach of patent or something like that. And Microsoft lost this case. Now, you can tell that they were planning on losing this case was because by 2001, Microsoft had already unveiled their own replacement to Java. Who knows what I'm talking about? Yeah, .NET, right? So .NET, like Java, is a managed environment for running your own code in a medium-level virtual machine. This is basically the same as Java. It's since then been implemented for Unix-like systems in a piece of software called Mono, which can be done because Microsoft actually specified the .NET system quite well and provided free licenses for anybody who wanted to implement it. And they actively encouraged implementers to produce their own implementations. And at the center of .NET is this thing called the Common Language Infrastructure. Now, this is something that's quite different to how Java went about doing things. It defines an important bunch of features that you'd want to have in a programming language, and they're normally implemented as part of a language. These are things like exception handling, memory management, and bytecode format. These all tend to be handled by language-specific interpreters on other platforms. But .NET took these things out of the languages themselves and made it in a different piece of software. And they released with .NET a language called C#, and C# almost kind of sort of looks like Java, not quite. But the point was that even though they released C#, all of the features that came with .NET were done in a language-independent fashion. So if you could do something in C#, then you could do that in any language that targets the .NET infrastructure. So you can have a whole bunch of compilers for the common language infrastructure, and these languages can all interoperate with each other. You can have a piece of software that includes C# code, you can include Visual Basic code, you can include C++ code, all in the same project, and they could all deal with each other. And as it turned out, .NET was a much better deal for the hordes of Visual Basic developers that were out there, because they could finally release a version of Visual Basic that targeted a managed infrastructure. So Visual Basic developers finally got things like decent memory management, which basic programmers had never cared about, which is why all the Visual Basic code before .NET came out had memory leaks, because the memory management in it was crap. But Visual Basic .NET let people develop Visual Basic code for .NET, which meant they could ease people over to a slightly more sensible programming language like C#. And because Microsoft were really, really smug, they decided they could also prove that C++ would run in a managed environment, which nobody said that they could do beforehand. And then because they really wanted to prove a point, they also made a language called J#. Now I wonder what the J stands for. It stands for Java. The language is identical to Java, except that you have the .NET class library instead of the Java class library. So if you're a Java programmer, all you'd need to learn is a whole new set of APIs rather than a new language if you're coming over to .NET. The unintended consequence of having this language independence, though, was that it's really, really easy to develop languages that target the common language infrastructure. And as a result, you can code in just about any language you would particularly want to. You know, there's Ruby, there's Python, there's Fortran. There's even lolcode.net. You can write all of these on .NET, and your code would interoperate with any code that targets the .NET infrastructure, which I think is a vast improvement over what Java did. So what's bad about this? Well, because it's Microsoft, they wanted it to work on Windows, so they give you .exe and DLL files rather than the easy-to-distribute library code that Java gives you. This is particularly funny on Linux and Mac machines, because the specification says that if you compile a piece of software for the common language infrastructure, a binary has to be called .exe. So if you can tell if something's written for .NET on a Mac because it has .exe on all its files, which is something you don't see normally. Amusing. Go look at it. So in summary, there were several things that .NET had. The most important one was that it adopted Java's idea of a managed environment, but made it such that multiple languages could target it. And what this meant was that developers weren't restricted to one language. They could take advantage of their Visual Basic developer base, but the consequences were that people could come and develop their own programming languages. Right? So, the second thing I want to talk about is JavaScript, which, despite its name, has a much more tenuous relationship with Java than .NET does. In fact, JavaScript has practically nothing at all to do with Java. So I'll just let you read this. I don't know what it means. It came with the first version of Netscape. So JavaScript was written by the developers at Netscape because they wanted there to be a programming language that could run on web pages. As far as I can tell, the reason why they chose the name JavaScript, because it has nothing at all to do with Java, was just to build upon the hype of JavaScript at the time, because this was released in 1996, 1 year after Java had come out. And the idea was that you'd be able to write client-side scripting, because the only way you could do that at the time was through Java applets. And anybody who's ever developed a Java applet knows that these weren't particularly good. Notably, it's a failure of JavaScript to completely replace Java applets that resulted in Flash happening, but that's another story. So JavaScript was cool. It let you pop up dialog boxes when you got your forms wrong and stuff like that. It let you do really, really simple bits of interactivity in web pages. And this is what people saw before 2004 for JavaScript. And then this happened. Who here has used this piece of software? I'm sure that you have seen this piece of software before. I think basically everybody has a Gmail account, right? This was released on April Fool's Day in 2004, along with Google's planned Moonbase announcement, I think. And Gmail was really the first demonstration that JavaScript could be used to build really huge, fully featured web applications. And these were just as good as, if not better than, the equivalent applications on the desktop. And I think it speaks volumes of what Gmail was able to achieve, is the fact that nobody really talks about web pages anymore when they're talking about developing for the web. People talk about web applications. The problem with this is that JavaScript, at the time, the platform JavaScript sucked really, really badly, and I think the language itself still does. Since the demise of VBScript, which was Microsoft's answer to JavaScript in the late 1990s, that really only ran on Internet Explorer, JavaScript is now the only language that will execute within web browsers. So JavaScript as a language has a monopoly on code that can run on the web. The problem is that JavaScript at the time was really, really, really slow and not suited to developing full-scale applications, because nobody had ever done it. So a few years passed, and then there was this great big arms race between the developers of various web browsers, including Safari, Firefox, and Chrome. Each of the developers of these web browsers came up with their own plans to develop new JavaScript virtual machines. The one that came with Safari was called Squirrelfish, that was its logo. Firefox had a product called TraceMonkey, and Chrome has one called V8. And as new weekly builds of these browsers happened, there were massive advances in JavaScript performance. This is looking at Firefox's JavaScript virtual machine, the one that existed before the current one. And so their test suite took 20,000 milliseconds or 20 seconds to execute back at version 1.5, and took about a quarter of that by version 3. To give you an idea, that's 2005 at that end, that's 2008 at this end. So that's a 400% increase in speed over a 3-year period. The take-home message is that JavaScript itself is now really, really fast. This has mostly come from investigating things like just-in-time compilation, which was pioneered by the Java virtual machine back in the early 2000s. Basically, for 3 years, the biggest tech companies working for the web spent heaps of resources in improving execution times for interpreted languages. And this really paid off for JavaScript. It went from being a really dreadful language to code in performance-wise to being just as good as even compiled Java code. Languages like Python, which used to be really good, relegated for quite some time, that started to improve with projects like PyPy. And JavaScript is so fast now that developers are even working on their server-side code in JavaScript. You may have heard of Node.js, which is basically a web framework and server for written in JavaScript. And so the problem that I see with JavaScript is that it's still a really, really poor language to actually write code in, but it's now the language that's entrenched in browsers. And it's now basically the best interpreted language there is in terms of performance. So in the past few years, there's been this community of developers who've been working on so-called alt.js languages. And these are basically languages that target JavaScript as its execution platform. So these may bear no resemblance whatsoever to JavaScript, but they have compilers that output it. And as it turns out, JavaScript is a general enough language, because it's so bad to code in, that it's a surprisingly good target to write languages for. So there are languages like Coffeescript. Coffeescript is a really lightweight layer that sits on top of JavaScript that has things like concise function definitions. The code on the left is Coffeescript, the code on the right is the equivalent JavaScript, and it produces clean, readable JavaScript. So it's easy to read, and it makes development for JavaScript less complex. If you're a fan of writing stuff for Apple platforms, there's Objective-J. Somebody has added a type system that's directly from Objective-C, as well as Objective-C's message passing runtime on top of JavaScript. And as it turns out, as long as you're not calling too many APIs that are directly written for Cocoa or iOS, your Objective-C code will actually work in Objective-J. It's basically the same language. And if you're particularly insane, you should check out Inscripton, which is a backend for Apple's LLVM compiler. So you give LLVM your C code, and it outputs JavaScript. Right? So I've seen a proof of concept for this, where somebody has compiled the CPython interpreter into JavaScript, and it runs within your web browser. So it turns out that JavaScript actually works really, really well as a compilation target for programming languages. And you should check out altjs.org. It has 6 pages worth of programming languages and various tools that all target JavaScript. So you're really not particularly compelled to write JavaScript if you're trying to write code for the web. My friend Brian McKenna gave a talk at linux.conf.au this year about altjs. You should check out his talk. It was really good. So in summary, JavaScript started its life off as a single language with a single interpreter. But they put in lots and lots of research for it, and they made its runtime performance improve greatly. And now it's not only amazingly fast, it's also fast and general enough to be useful for other programming languages. The third thing I want to talk about is Android. And this is even further away from Java than JavaScript is, which is strange because when I went to OSCON last year, I heard this guy who used to be an enterprise Java developer talking about how he thought that Android was the realization of Java on the mobile. And when you write code for Android, you write it in Java. It looks something like this, right? That's Java. But if you look at this diagram that Google provide, which is a layout of how Android works, there's no mention of Java at all to be found. I mean, look, this is what all these things are, and there's no mention of Java whatsoever. See, there are ellipses, right? It's an important part of Android. So this yellow bit here appears to be important. There's this thing called the Dalvik virtual machine that runs on Android. Now this isn't a Java virtual machine. In fact, it's a completely different virtual machine. It takes a different machine code, but it's designed to be lower level on ARM CPUs. So instead of compiling code that targets specific versions of ARM CPUs, it uses a virtual machine that is general enough to all of them. And this is in contrast with the JVM, which runs on all manner of processors and isn't particularly specific to any of them. So the thing that's particularly good about Java is that there are heaps and heaps of developers out there for it. There's lots of code that's written in Java, and being able to leverage all this code is a good thing. So it may be instructive to take a look at how Android does this. Here's this fantastic diagram of the build process. I expect you to understand it and answer questions about it at the end of the talk. Or we can just look at this bit here, which is the important bit. Rather than implementing its own compiler for Java, you take some compiled Java classes from a Java compiler and perhaps some class files from other sources, and you run it through this utility called dex. And this produces Dalvik bytecode, which unlike Java bytecode is actually stored in a single file rather than multiple class files. And the take-home message from this is that Android is distribution compatible with Java. That is, you can take code that was written for the JVM, was compiled by somebody years ago without knowing that Dalvik would ever exist, and still have it target the Dalvik virtual machine. And what this means is that there's a massive base of pre-developed code out there for Android, but it runs on a platform that it wasn't designed for. And that's a huge advantage for developers who want to port their code to Android. So in summary, what they did was take Java the language, but write a new virtual machine for Java that was better suited to mobile devices, and they made it distribution compatible so that they could take advantage of Java code that's already out there. And so the result of that is now Dalvik is a virtual machine that is an alternative to the JVM that can be used instead of the JVM in places where you want better power management, for example. And so with that, we turn our attention back to Java itself. What is it that Java could learn from the existence of these platforms that came after it? Well, we learnt from .NET that it's possible to create a managed runtime that isn't language specific. And through developing the common language infrastructure, Microsoft accidentally fostered a community of language designers all centered around .NET. And with JavaScript, by keeping a really general machine code, but making their interpreters really fast, Java has basically become the de facto machine code of the web. It will probably be the case that in a few years, nobody will be developing JavaScript on their own. Instead, they'll be developing in alt.js languages like Coffeescript. So the question is whether or not there are alternative languages for the JVM. And the answer is, well, there is. The first of these is basically a simple extension of Java called Groovy. Most existing Java files are valid Groovy files, but Groovy itself isn't as strict or as verbose as Java if you don't want it to be. And everything that you compile for Groovy itself compiles down to valid Java class files, which means you can use Groovy files in the same, within your Java code if you wanted to. And an attempt to create a completely different language is Scala. And this is probably the one that's gaining the most traction in JVM land at the moment, and will probably be the language that overtakes Java itself as a preferred language for targeting the JVM. Now, what's notable about languages like Groovy and Scala is that their code structure ends up resembling that of Java class files. Groovy and Scala code can be interchanged for Java code, and Java code can call Scala or Groovy code, and vice versa. Not every JVM language, however, ends up operating like that. Clojure, that's spelt with a J, is a Lisp variant which runs on the JVM. And that's very much its own language. It doesn't produce code that resembles Java class files unless you explicitly tell it to, which is good and bad in terms of interoperability. It means that you have code that runs on the JVM, but it doesn't necessarily participate in the Java ecosystem. And as well as alternative languages that target the JVM, there are also languages that are just designed as simple extensions over Java itself. The one that I've been working with myself for the past couple of months is called Extend, which is part of the Eclipse project. And it's basically a Coffeescript-like language for Java. It compiles down to valid readable Java code. So it means that you can check this into your version control if you need to have valid Java code in any case. But the alternate languages for Java community isn't nearly as strong as it is in .NET or JavaScript. Because you need your languages to be useful in this case to produce class files that resemble Java class files, which means that you need to have an object-oriented structure in the same way that Java does. And this can be seen with Groovy and Scala, which were by far the most popular alt.jvm languages. They're still completely object-oriented, but this is not the case with, say, .NET. The other thing that I think we might be seeing as Java developers is the proliferation of more virtual machines. We've seen that it's possible to take virtual machines which allow for runtime optimization of applications. Just as using just-in-time compilation on Java increases loop performance, so could it be done for other languages. An example of this is LLVM, which is not something that targets Java. Instead, it's a replacement for the GNU toolchain for C and C++ and languages like that. The code gets compiled for an intermediate virtual machine, which can then be runtime optimized. And the early signs with LLVM, it's still a relatively young project, is that despite not being native machine code, it can produce code, output code that is quicker than the equivalent machine C code for meaningful test cases. The other thing we might see is that as power consumption in data centers becomes more of an issue, ARM-based servers will come to exist. And we now have a virtual machine for ARM devices, which is far more efficient than the JVM. And so it will probably be the case that we'll start seeing the Dalvik virtual machine that was written for Android come into its own on ARM-based servers. There are already projects out there that are trying to decouple Dalvik from Android itself. So that's the end. I hope I've given you some sort of idea of how programming languages and software development tech has evolved over the past 20 years. Hopefully it's been instructional. Are there any questions?
How does HTML5 fit into all of this kind of landscape?
HTML5? No, HTML5 isn't really a programming language,
Yeah.
right?
It is going to affect the distribution.
Oh,
applications.
right. So in this case, HTML5 isn't particularly a useful technology without JavaScript, obviously. If you're trying to produce dynamic web applications, you need to have a programming language attached to it. And as I said in the talk, the de facto machine code of the web is now JavaScript. So what's going to be more interesting is to see whether or not people are developing applications purely in JavaScript or whether or not there's going to be a movement to alt.js languages. I certainly think there is going to be, because it provides a better development experience for developers, because you can add things like strong typing for people who prefer to have a typed language. Or it will permit development in other languages other than JavaScript that they might want to develop in. There are things like Python and Ruby interpreters that target JavaScript, as well as compiling alt.js languages.
So you reckon JavaScript won't be supplanted by anything else?
Well, the thing is that JavaScript itself, it's the language that is coupled into every web browser now, right? IE6 runs it, that's starting to disappear, but all versions of IE from then on have started to become faster and faster. And there's now no reason why you need to build in more languages into web browsers, because the alt.js community is proving that JavaScript is a really good target for languages to target to. So you can compile other languages down to JavaScript. So there's no reason to have anything else. Beanut.
We heard of native client.
Native clients. That's the thing that Chrome's doing at the moment, isn't it?
Yeah.
Amongst other things.
Google is. Yeah.
Yeah. So having natively executable code exist within the browser. Yeah, sure. I mean, it's sandbox, but it's something that would, well, I'm sure there's a good reason for them to do it, but I'm not sure it's going to take off in the same way that JavaScript has, because it's something that, as I understand it, you have to directly approve for code to be loaded at a given time. It can only target a specific processor at a given time, which means that it's going to be something that can only run on desktop operating systems on a given processor architecture, which might not have been a problem several years ago, but now we're starting to see all these useful mobile devices that are running on ARM CPUs. So there's a need to have a processor-independent machine code, and I think that JavaScript is pretty much it now. Other questions? I was hoping I'd raise some interesting ideas that you'd want to comment on. Yeah? When's the next talk? Probably after Easter. Not sure. We'll announce it when somebody volunteers to give it, obviously.
I'm just wondering why iOS and OS X avoids JavaScript.
The reason why iOS and OS X avoid Java is because the user interface library for OS X and iOS after it is is heavily based and uses features that are built into the Objective-C runtime. And if you compare Objective-C's object orientation model with those of other languages, it's a completely different beast. It makes absolutely no sense to be able to compare the two of them. It's completely different. Apple did for quite some time try to release Java bindings for Cocoa, which is their UI library for OS X. And they gave up after a few years because it was just impossible to keep up. There was no way that they could completely use the features that Objective-C provided them, but keep it compatible with Java. And so they just gave up after a few years and deprecated it. It's just that because they chose to use Objective-C as their preferred programming language, other languages that didn't talk to Objective-C well couldn't keep up. You can compare that with Python and Ruby, though. There are translation layers for Python and Ruby which talk to Objective-C quite well. And so Python and Ruby are still first-class languages for developing Mac code, certainly, but not iOS code.
The Objective-C runtime is just a few small functions, and
It's
so binding it's not too hard.
It's a few small functions, but you can't really write the way that Java, because Java expects you to have a statically defined interface for classes. It's hard to deal with the way that Objective-C loads things at runtime in a way that makes sense without statically generating bindings for all the classes that exist in an Objective-C library. It's hard. It's an oversimplification of things, but it is basically the reason why Apple dropped Java.
It's also just a ton of effort on their behalf.
Yes, because they'd have to generate static bindings for everything that came with Cocoa, which they didn't have to do with other languages. Yep.
Does JavaScript itself impose any sort of restrictions on the type of languages you can implement, like the way the JVM does?
Well, the thing is that JavaScript is pretty much a free-form language in terms of how you can structure your code. So with Java, you have to compile everything down into class files, and those class files they resemble a class that is written in Java source. Whereas with JavaScript, everything is executed from the top down. It's read in the order in which it's defined. And there's no defined point of entry other than the top of a script. So you can basically compile anything you like down to it and define its own entry points and its own structure and things like that. Which means that you can basically compile anything down to JavaScript, as has been proven by the Inscription thing, which is basically any piece of C code that you write can target JavaScript as a backend using LLVM, and that's pretty cool. Anybody else? We're out of time? Okay, well, I understand there's a barbecue on now, which is going to be at the Grassy Knoll or something like that. So I all strongly encourage you to get out there and have some sausage and drinks. See you at the next talk. Thank you. Yes? I'll be posting a recording of the video, a recording of the talk later on after the talk is gone, after I clean it up a bit. All good? Cool. Thanks all for coming along.
Well, barbecue didn't go first, right?